It's 10, 1 minute. So let us wait for 1 minute and then we'll start.
Sure.
So good morning, you all, and I welcome you all on the second day of the QIQT. And as you can see in this session, it's mostly the talks are on the quantum optics kind of things. And there are three speakers, and the first speaker is Dr. Vivek Vyas from IIIT Vadodara, and he's our own student, so he was here in IIT for a long time. So with this background, I invite Vivek to present his lecture. Vivek.
Yeah, thank you, sir, for a generous introduction. It's always very nice to, physically come and speak at IISER Kolkata. But if it is not possible physically, then certainly in the virtual mode. It's my alma mater. I have a special affection for this place. So today I'm going to talk to you all about Bose-Einstein condensation of light and what is called the Dicke superradiant transition. If you are not familiar, don't worry, we'll understand everything. We'll try our best to make sense of these words. So let us sort of slowly begin by just recapitulating what we know about quantum harmonic oscillator. Now, at some point, in our college or maybe beyond masters and all, we sort of look at one of the easiest models that one learns to solve with the harmonic oscillator. And we know that the Hamiltonian is given in this form. So you have the kinetic energy part and you have the potential energy part. Potential energy part is quadratic. So classically, we know that you can take this energy can be continuous, depending upon how much amplitude you begin with, how much was the initial displacement that you are giving to the oscillator. That decides how much energy you have pumped in. But we learn in quantum mechanics that, in quantum system, that's not the case. The energy is discrete. This is how we sort of learn it. And it can only be increased. The energy of this oscillator can only be increased in amounts h bar omega. So either you can be in one level, or you can be another level, or another level, or another level. But you cannot be in between. No, that's the beauty of quantization. And a more algebraic way, there are many ways of understanding this, but there is a nice algebraic way of understanding this in terms of what is called the raising and lowering operators. I'm sure you would have come across these operators. In terms of x and p, you write it in this form. You can say that you are just making a complex. You are treating x, you are treating p as your y coordinate, and the way you write complex numbers, x plus iy, you do the same with x and p. So it's like you are treating phase space as a complex plane in a way. But then you have to remember that in quantum mechanics, x and p are not usual variables. They are not the normal variables which you multiply. They're operators, and hence they don't commute. They give you IH bar. So ordering has to be kept in mind. And if you keep in mind, if you do it properly, you will find that A and A dagger, A and its conjugate, the commutator is equal to 1. And you have other relations. So if one sort of plays around with these operators carefully, one learns that the raising operator, A dagger, takes you from ground level or the ground state, which is depicted here, to the first excited state by its action, modulo some constants. We have ignoring these constants. We want to just understand the concept here. Similarly, if you apply a dagger on the first excited state, it will take you to the second excited state. If you apply I mean, if you keep on applying it, you will climb up this ladder. On the other hand, the conjugate of A dagger, which is the A operator, does exactly the opposite. It brings you down the ladder. So that is the beautiful role of these two operators. And excuse me. Algebraically, it can be also understood using these two commutators. In case if you are not familiar, it's a nice exercise to sort of begin with. So, harmonic oscillator in nature, we see in many places. So many systems approximately behave like harmonic oscillators. Here we are going to see, or we are trying to understand that how photons in a way behave like oscillators. Sounds very counterintuitive, but that's indeed the case. And a great deal of this talk, or in fact most of the talk, is about appreciation of that only. Can you think of photonic systems as a bunch of oscillators? If you can, then it can give rise to very interesting phenomena. So what are photons? Everyone knows that photons are quantum of electromagnetic field. Well, what does it mean? That electromagnetic field, like in case of this oscillator, it does not have continuous energy. Of course, at our length scales, in our daily experience, we don't feel it. But if one does careful experiments, you find that the energy, electromagnetic energy, comes in packets. And if you happen to visit a laboratory, like there is a laboratory in the place where I am staying called the Physical Research Lab, there are people who do experiments where they see these kind of single photon, a single quanta they are able to detect. So it's a reality, but you can there are indirect ways of confirming it. Direct ways, in our daily experience, there are very few, but you can believe it for now, that this is indeed the case. So essentially what happens that if you sort of have a laser source, kind of laser pointers that you would have seen in presentations and other places, the light that is emitted by such a laser source is strictly monochromatic. So that's the beauty of laser, that it emits light of strictly one wavelength, let's say lambda, and frequency nu. Then you have the angular frequency, and correspondingly, you can, the Einsteinian relation tells us that how the energy of that photon is related with the angular frequency, and how the momentum is related with the wave vector. So these are very famous relations due to Einstein, almost 100 years or more, old relations. So the point is that if you would have a detector somewhere here, and if you would be measuring the energy of the light that is coming down to you, it will all the time be in multiples of h bar omega, because you can have one photon, you can have two photons, you can have three photons. See, you cannot have a half a photon. That's not allowed. Okay. So there is some noise. Can somebody switch off the microphone? Yeah, thank you. Yeah. So if one tries to measure the energy of the radiation that comes out from this laser source, then one would find that it is actually h bar into omega into just number of photons. All you have to do is you to just count number of photons that are detected. And we have these very excellent detectors, photomultiplier tubes and other solid state detectors, which can do this job very nicely. So, number of photons can be represented by this object A dagger A, which I forgot to mention. That A dagger A here tells you on which level you are. This object A dagger A. If you apply it on a state, like if you apply it on the state 2, then it will give you answer as 2. So it only tells you on which level you are. Like, it does nothing. It just tells you where you are. What is the number? So similarly, here you think of for this photonic system, you construct this kind of an object, which gives you number of photons. So the energy level, these numbers in oscillator were giving you the energy level, which level you are. Now in the photonic system, they will give you the number of photons that the system is having. And of course, the destruction operator will destroy a photon. It will take you to the lower level. It will decrease the photon by 1 unit. And a dagger operator will increase the photon number by 1 unit. So kind of, it's a neat algebraic game, sort of, if you want to think it in that way. So the Hamiltonian would simply be a dagger, and omega subscript is to remember that we are dealing with photons of frequency omega multiplied by the energy. But in reality, you don't work with strictly monochromatic light. We have plenty of other light sources, like a thermal source like a bulb, or you have CFLs, fluorescent light sources, sunlight, of course. You have daylight coming from the skies, from the clouds, and certainly they are not monochromatic. They have radiation consists of all the frequencies. It's a continuous distribution, peaking at some particular value. So the question arises that if one is dealing with such a case, then what would be the energy, and what would be the Hamiltonian? Because we just want to understand what happens. So, well, what one has to do is that you have to just take sum over all the energies of all the frequencies of photons. You just sum it up, and that's what you do. It's a straightforward, simplest way of doing it. So, in other words, you multiply the energy at one frequency, multiply it with the number of photons of that frequency, and sum over all the frequencies. Or equivalently, instead of working with omega, I can work with wave vector, because anyway, omega and wave vector are connected to one another. This is the energy, energy and momentum are connected to each other, we know. Similarly, omega and k are also connected to one another for light, So if one sort of translates this, one gets the Hamiltonian, where this term is essentially this h bar omega, and we have this number operator again taking this form, that a dagger of k wave vector into a of k wave vector. Okay, so we just see that this total system of radiation consists of a large number of oscillators. Like, each of them is an oscillator on its own, and you are just summing over all of them. But they are decoupled, they are disconnected. Each oscillator is independent. A very, very important fact. So when one is dealing with these operators, some certain care has to be taken in mind, that the way you think of them is that a dagger of k creates a photon with momentum h bar k. So, but it does not affect any other case. It only affects the k that you are interested in.
There are some questions on the chat box are coming, so if you like, you can respond.
Oh, okay. I'm not able to see them. Just a minute. Okay. Just a minute. Let me open the chat box. Yeah. So how are two photons very closely bound, say, of angular frequency omega, different from one photon of frequency 2 omega?
Maybe what I can suggest, you finish, and then in the end we will take
Sure,
out.
sure. I think that would be better. Okay. So, yeah. So the point is that, like, if you apply A of K operator, it will only increase the state of the system with one photon with wave vector K. It will not, it will not see anything else. Even if there are other photons in that state with other momentum, like K prime or P or Q, it will just not affect them. Okay. Similarly, A of K destroys a photon with momentum momentum h bar K. Yeah. So basic idea is that they are like these each wave vector, photons with different wave vectors are different entities in a sense. At least in this case, they don't talk to each other. They have their own operators. They have their own small worlds where they're living. Okay. And just like we had, these very famous, commutation relations of harmonic oscillator, because we are having a bunch of oscillators here, so we'll have a natural generalization, like a dagger relation with different wave vectors is zero. If K and K prime are not same, then this delta function does not contribute. So it is zero. And if they are the same, then only there is some non-trivial action. So you can say that why there is this delta function and all. Well, that is more of technicality sort of. When you want K to be continuous function, and that's why you have to work with this Dirac delta. You can also work with Kronecker delta, which is not like singular like this, but then you make K to be discrete. You put a periodic boundary condition or something. And so I will not have time to discuss into the technicality of how do you get it, but you can consult any sort of simple book on quantum optics or like book like Schobel, Advanced Quantum Mechanics, or Sakurai, or book by Ashok Das, for example, on field theory. If people are interested in that side, they will find a very neat derivation of this. Actually, this is very simple, but it may appear slightly out of the way right now to some people at least. Yeah. So, and here you can ask this question that what is the total number of photons? Well, total number is just addition of numbers in each mode. So with each wave vector, you just ask how many photons are there in mode K1, how many vectors are there in mode K2, and you just sum over them. So that is just sum over all these number operators. Okay. So this is, what we have understood till now is just that a photon gas or sort of collection of photons sort of behaves like a bunch of oscillators, nothing more than that. So this is more of a mathematical game that we have played till now, till this point. Essentially, we are not like asked for much of physics. Now let us ask some physics questions. How does this photon gas behave? What do we mean by, what is the physical scenario that one would have in mind? Well, the scenario at least that I have in mind is this case that I have a metallic sort of a box, some kind of a vessel which is of a very good quality, and I put it in on some kind of a flame so that it's gradually heating up, and I'm assuming that the flame temperature is not going to melt the box, just to be safe. And I'm waiting till this whole box is in equilibrium with the flame temperature. Okay. Now the point is that the box is empty from inside, mind you. I'm assuming that there is only vacuum, like there's nothing inside. It's a good quality vacuum. Okay. But we know that when you heat up a system, it will emit thermal radiation. Like when you heat up, you have radiation coming from sun to us, heats up. When you go outside in sun, you feel the heat because of radiation. It is not because of conduction, right? Because you have these infrared microwave energy photons, which are absorbed by your body, of course, ultraviolet as well, which, heat you up. So similarly, inside this cavity, there will be photons. There will be radiation emitted from these walls. All these walls, and they are going to emit radiation. Of course, then some of this radiation will also get absorbed. They will also get absorbed by the walls. And eventually, if you wait for sufficiently long time, there is an equilibrium. Certain number of photons will be absorbed by the wall, and certain number of photons will always be emitted by the wall, and that number will be roughly the same. So that photon number is almost here inside. The photon number is more or less constant. It can be mildly fluctuating, but more or less it will be a constant. Okay. So in that case, you can say that one has created a photon gas inside this cavity. There are just photons which are passing through each other. Photons don't interact with one another in absence of any medium. You have one ray of light. Like if you can do this experiment with your in your laboratory or at home, you take one laser source and pass another source through the beam of first one, and nothing will happen. So that's the beauty with photons, that they pass through each other. Only at the position where both the beams intersect, there will be a linear superposition of electric fields and magnetic fields. But the moment you pass that location, nothing happens. Okay. So photons don't collide with one another. In other words, they pass through each other. Okay. So this is a very funny kind of a gas. Your usual gas of air molecules or any other gas that you know of, it does not behave like this. Or even electrons. Electrons repel each other, they scatter each other. So this is a very funny gas, in a sense, very, very special. And we can also remember that photons are bosons. And what are bosons? Well, bosons are the ones that particles which can, you can populate them in one quantum state, unlike electrons or neutrons or many other particles that are very popular. Photons are very, very good bosons. So then question arises that what if I lower the temperature of this heat source? I gradually cool it down. Instead of heating it up, I connect this object to a high efficiency refrigerator, which can lower the temperature. And I'm assuming that the refrigeration capability available to me is of extraordinary kind that I can approach absolute zero. Okay. Then normally one would say that all these photons, their energy will eventually get lowered. So this photon gas inside will be described by this Hamiltonian. This will be the description of this photon gas. And what the lowest energy state of this Hamiltonian is the one when wave vector is equal to 0. Okay. And I'm assuming that I can take this limit. My box is sufficiently large. I mean, just to be mathematically safe. If it is finite, then I'll take the minimum value that my box can have. Basically, I want to minimize this k, because that's how I can minimize h. And of course, I would expect that k equal to 0 state would be populated. All these photons will gradually settle in that k equal to 0 mode, and I would get a very interesting state. But that does not happen. If you do it yourself, that does not happen. And the reason is that the photons can be absorbed by the walls. So nature chooses to minimize energy or Hamiltonian, not only by minimizing k, but also minimizing this number, which is variable. So nature says that, well, why should I only minimize this? I will also minimize this. And the minimum number is 0. So at t equal to 0, what you get is 0 photons. So you don't get anything interesting. Excuse me. Yeah. So oops, my goodness. Yeah. So in 1989, Raymond Chiao was concerned with this kind of a problem. And he suggested that instead of working with this kind of a metallic cavity maintained at a fixed temperature, let us work with a cavity which is made up of mirrors. So what he had in mind is, suppose you have two mirrors, and let's all these walls be maybe of it can be metallic, but it's of a high quality mirror. We have done a nice silver coating or something on the inner walls, so that photons are almost 100% with 100% efficiency, they are reflected back. Okay. And if you make it cylindrical, then predominantly photons are going to bounce back and forth. Very little momentum is on the tangential direction. These are idealizations, of course. Well, then the problem of absorption by the walls can be avoided. Then the photons are not going to be absorbed by the walls, almost. But then the question is that how do you thermalize them? How do you cool them? They have to be this. You will have a photon gas by somehow, like you may make a hole here, populate this cavity with some photons, like shine some laser, and then very quickly you close it. So then there is a photon gas inside, but that gas is not in equilibrium with the reservoir. You need a thermal reservoir, zeroth law of thermodynamics, as per zeroth law of thermodynamics, to have equilibrium. Okay. So his point was that what one should do is that one should, in this cavity, introduce some medium, which I have sort of indicated by this yellow sort of screen. Just a diagrammatic way of, sort of showing you. So Chiao's idea was that if you introduce a medium, then these photons are going to interact with this medium. And medium temperature, if you can control somehow, if you can manage, then eventually photons, see, this medium is maintained at some temperature T. That's an assumption. Photons which are interacting with this medium eventually will also reach this same temperature T as per zeroth law of thermodynamics. And if I gradually decrease T, this will decrease the T of medium as well as photon. So eventually I can try reaching T equal to 0. But there are many catches here. First of all, if there is a medium, then medium can absorb photons. Right? That's what happens when you cannot see light coming from faraway distances, because air, there are aerosols, there are dust particles in air which absorb light, which scatter light. And you cannot see starlight coming from faraway places, because although the outer space vacuum is very high, of a very high kind, but the atmospheric, you have a atmospheric absorption of light. So similarly, if you introduce a medium, light is going to get absorbed. And how are you going to ensure that photons number is still the same? Basically, you will have the same problem as this case here by introducing the medium. So the way out was it took a lot of time for people to understand nature of this medium and photon interaction. And the way out was that we introduce this medium. We will have a kind of an atomic medium or a molecular medium, where you will have these, let me draw and maybe I'll tell you. Yeah, so where you will have these, atoms may have these kinds of levels, some levels, energy levels. And the point is that if your photons, they fall in this region, if the energy matches, the photon energy is h bar omega, if it matches with this level, then there is a rapid absorption. This is called the resonant absorption. So almost all the photons will be absorbed. But if you have photons whose energy is much larger, then let's say if you work with this kind of energy separation, then it turns out that the absorption is very, very less. There will be absorption. It's not that it's zero, but it will be very, very less. Or in other ways, if your atomic level separation is this, and if your energy h bar omega is much less than this separation, then you know that my atom cannot absorb energy because just the separation is too much. So in that case, what will happen? That there will be only scattering. No, there is no resonant energy transfer between the medium and the photon. It's only like energy preserving sort of scattering in a way, if you want to use this word. And that can lead to thermalization, which means that you will have this photon gas inside this cavity, which will have a thermal distribution, a Maxwell-Boltzmann distribution, or correctly speaking, Bose-Einstein distribution. And medium will not affect the number of photons in the cavity. Number will again be more or less constant. There will be some losses. Losses will principally come from the mirrors, because no mirror is of 100% efficiency. There will be some losses. Similarly, there will be some losses in the medium also. Some absorption will take place. But to a very, very large extent, your photon gas number here will be under thermal equilibrium. It will obey the laws of thermodynamics. No. So this was achieved in this proposal was given in 1989. They tried with atomic gases and all, but they failed. Only in 2010 onwards, a group from Germany in University of Bonn, they were able to realize such a proposal. This experiment, very careful, very beautiful experiment. And they were able to populate the lowest energy mode in this cavity, which would be like k equal to 0, the vector k equal to 0 for its analog. So in their case, it was the TEM00 mode, because their cavity was having a different shape, and that was the lowest mode. And they were able to generate what is called the Bose-Einstein condensation of photons. So you have large number of photons populating a one cavity mode. This was a big achievement. And in that case, this was the mode that was populated. You may say that, well, what is so special about it? I mean, SN Bose anyways said that, BEC is possible for all bosons. I mean, Einstein actually gave that concept. SN Bose gave the distribution. And well, anyways, that was done in long back, 1924, I believe. So what is the big deal about it? Well, the big deal about it is that it was the experiment. They were able to do it. Otherwise, and it was not even clear that whether photon gas will, whether it will go to BEC state or not, that itself was questionable for many other reasons other than this. So that was one thing that was of, you can say that people rejoiced when this experiment discovered the condensation of photons. The question arises that how do you describe in language of quantum mechanics such a state of photons? Well, the answer is sort of very simple, that the way you describe is that you describe in terms of what is called a coherent state. Why coherent state? Because you want your number operator should get only the contribution from k equal to 0 state. It should not have any contribution from other case. And the contribution coming from k equal to 0 state should be very, very large. Technically speaking, it should go to infinity as volume goes to infinity, because that is the thermodynamic limit. So number goes to infinity as volume goes to infinity, but n by v, number of particles by volume, is finite. Okay. So if you go by, if you sort of think about it, if you spend some time, you will find that the only way you can depict this state is by postulating that the state of the photon at t equal to 0 is given by the state called omega, which must be an eigenstate of this annihilation operator. A of k is equal to alpha. Alpha is a scalar. This object is a vector. It's an operator. This is a scalar. And this alpha of k must be a constant times delta function of k equal to 0. Because remember that the only contribution, non-trivial contribution, can come from k equal to 0 state. Because there are no photons in any other states. That's what BC state means. So you use this object, you use this equality, you plug it in here. So you will have mod alpha square, which is like constant square times 2 delta function. And then you have to sum over all k, because this n involves sum over k. You can do one summation. When you do another summation, you will get delta cube of 0. If you're able to follow and if you're able to do it, delta cube of 0 is actually the volume of the system. So the only way you can get volume is by this trick. If you don't take this and with this limit, you don't get this answer. And so when you take this volume of the system to be infinite, then the number also goes to infinity, but n by v is finite because there is a constant here, and when you divide, it is finite because this constant will appear here, which I'm not written. So this is the only way in which you can understand condensation, macroscopic occupation of k equal to 0 state. So, well, fine. So what? I mean, you have understood. We have found a state, and we have discovered a way of understanding it. So, what is so big deal about it? Well, the big deal about it is that this number operator is not a very. It may sound very innocuous. It may look very sort of innocent, but it is a very non-trivial object. Why? Because first of all, number operator commutes with Hamiltonian. See, what do you mean by why should that be of interest? Well, when you have two objects which commute with another, you can simultaneously diagonalize as per quantum mechanics, which means that a state with fixed number of photons, a definite number of photons, also had a definite number of energy. Of course, it does has, because that's the way we started defining it. That energy is just with up to some factor is multiplied with number of photons. So a state with a definite number of photons certainly has a definite energy. So hence they must commute. That's the physical way of justifying that why number operator and Hamiltonian should commute. But the other way of looking at it is that when you have objects which commute with Hamiltonian, they generate symmetries. What do we mean by it? That you have angular momentum in hydrogen atom problem, for example. Let me write it here. In hydrogen atom, you have Lz commuting with Hamiltonian, and that generates a symmetry. So if you rotate the system along z-axis, nothing changes in hydrogen atom because the Coulomb potential is radial. It does not see these angular changes. Okay, and as a result, you have consequences. You have the radial quantum number. You have the azimuthal quantum number n. The origin of that quantum number comes from this. Similarly, this n generates a symmetry. Well, the symmetry generated by this number operator is not as physical to our. I mean, it's not physical in the sense that you cannot visualize it, but it is abstract. It generates certain transformations in the phase space. You can think of it that as if that we started with these P operator and we went to this X and P. I mean, it is sort of that as if you are moving in the complex plane. You are treating X plus IP as a complex plane, and number operator sort of is rotations in this space. Sort of. And of course, nothing matters because your Hamiltonian rotations in this space doesn't matter because n commutes with h. Okay, so it's sort of like rotations in complex phase space, sort of, if that is the way one wants to see it. But what this relation tells us that the state of the system, which is given by omega, does not respect the symmetry. Why is it so? See, if something would have been symmetric, if this was a symmetry, then this answer should be well defined. This operator n acting on omega. See, when you have an object, when it acts on a state, its inner product with another state should be finite. That's, when you get infinities, means you are doing some mistake somewhere, or you are taking limits which you should not have been taking. So a way of understanding, you can say, the mathematical way of understanding it is that the state of the system, omega, which is the ground state, is not respecting the symmetry generated by n. Another way, some people who are more, you can say, interested, they can do this exercise. And you will find that this would tend to 0. You are doing a small rotation. This is like not very different from this rotation. So this is like doing a small rotation around z-axis. This is like you are doing a small rotation or a finite rotation of angle theta in the complex phase space. And then you are asking that what happens to the system if I do that? And you find that the system changes, like it is not invariant. This should have been actually equal to 1. This object should have been 1. But actually it goes to 0 if you do it properly. And when you have this kind of a phenomena where a symmetry of a system is not respected by the ground state, then you say that you have a spontaneous breaking of symmetry. It's a very, very, very beautiful phenomena, very, very important conceptually. It appears in so many branches of physics. A whole bunch of condensed matter physics is just the whole phenomena of spontaneous symmetry breaking essentially gives rise to like 90% of phenomena in condensed matter physics. More very, very interesting phenomena in high energy physics also occur due to spontaneous symmetry breaking, the Higgs boson and whatnot. So in this manner, you see that spontaneous symmetry breaking now appears in this way, has appeared in the realm of quantum optics. And up until now, it was only a concept. There was no experiments to sort of compel you to think that there is such a phenomena, but this experiment of condensation of photons has now compelled you that, well, there is a spontaneous breaking of symmetry. So all this language of Goldstone modes and so on and so forth, everything comes into picture now into quantum optics. I don't have enough time to actually go into nitty-gritty details. I could, but then I fear that it will cause indigestion, so I'm not going to get into it right now. But you may think that, well, this is one of the model, like you just made a very simple model, photons. I mean, like it may be an artifact of a simple model. You have to come up with more physical model, something which is, if you can show that this phenomena happens in other cases also, then probably some people would be interested, they will pay attention to it. Okay, so we'll take up another model that's called the Dicke model, and we'll see that there also this phenomena happens. What is the Dicke model? Essentially, it's the same model like this, except that here you only allow for one cavity mode, like some fixed K. there is no other modes are allowed. You only populate one mode in this cavity. And again, you have two-level atoms which are only having these two levels. Of course, all the atoms have other levels. But when we say two-level atoms, we are sort of telling that light is going to only interact with these two levels. Either light is absorbed by the atom and it goes from this level to the next level, or the atom which was in the excited level spontaneously decays at some point and comes back to the ground level. Or there can be stimulated emission, that in presence of other photon, this atom also decays. So this two-level approximation is only a good approximation when light is near resonance, when this is the case, that h bar omega is close to this energy separation. Otherwise, it's not a good approximation. It will not give you good answers. So we are assuming that.
Vivek,
so remember, yeah.
Please
yes,
complete in 5 minutes, so we have 10
Sure.
minutes for discussion.
Sure, I do that. Yeah. So the point is that here we stayed away from resonance. Let us now take the case where we are near resonance. So that is given by the Dicke model, that we have relaxed the resonance condition, and then we have one mode, one oscillator, and then we have this bunch of two-level atoms whose energy separation is E, and we are assuming E to be close to epsilon. And then we have this, sort of interaction where you can create a photon by decay of an atom, or you can destroy a photon by excitement of an atom, and you sum over all the atoms. The sigmas are Pauli matrices, which I'm sure you would have known, or if you don't know, you can look it up. Very simple objects. This is the way you sort of just describe these bunch of atoms, and then you sum over all the conditions. So you can ask this question, but if you are near resonance, the photon number is not conserved. But that was the whole point. That's why you introduce a medium which is not near resonance. So then the point is that to get BEC, it is not only that you need photon number conservation. Here, what you need is a conserved quantity. If your problem has a conserved quantity, which is in this case, it is given by this. And by conserved quantity, I mean that H and Q commute, then Q is conserved. If you have only so much, then also you can have a situation where the photons get populated macroscopically. That means their average tends to infinity, and which also means that Q average also diverges, which is phenomena of spontaneous symmetry breaking. So in Dicke model also there is a spontaneous symmetry breaking, and that breaking is called the Dicke superradiant transition. It occurs below a certain critical temperature. But the point of this talk is to just, sort of to give you an idea that in two very different models, two very different scenarios, you see same phenomena happening. That is that of spontaneous symmetry breaking, which unifies them. You can use same framework, same concepts to understand both of them, and both have very different physics in a way, but the underlying unity of phenomena is same, sort of. So I think I have concluded my discussion here. I shall be happy to answer questions.
Yeah, so you can take first the questions in the chat box. And
yeah, just a minute. Let me go to the. Yeah. So what was? So Abhinav Dhawan has asked, how are two photons very closely bouncy of angular frequency omega different from one photon of frequency 2 omega? I am not able to understand this question. No. So, see, their energy. How are two photons of angular frequency omega different from one photon of frequency 2 omega? Well, their momenta are different. That's one way of understanding it. Let me take other question. Yeah, how K appears in the Hamiltonian, Komal is asking, is there any derivation? Yes, certainly there is a derivation. I mentioned it. If you can look at book by Schobel or any book where advanced quantum mechanics is touched upon, like you can look at Gottfried and Jan's book, or Sakurai's book, Advanced Quantum Mechanics by Sakurai. Several, any standard book where advanced quantum mechanics is discussed or quantum optics is discussed, you will get this Hamiltonian that I'm quoting. Yes, and then there is a question by Danish Trivedi. How do we justify saying that we treat photons as oscillators when there is no potential? Look, this is a more of a algebraic trick. You are using the algebra that you have discovered of creation and annihilation of harmonic oscillator problem into creation and annihilation of particles. I'm not saying that. It's just that the same mathematical framework is useful. Just like, you add two integers, you can add two matrices. Of course, addition, you can, matrices are different objects, but the concept of addition is same. Okay. Similarly, concept of creation and annihilation in terms of these operators is the unifying feature for harmonic oscillator and photons. Okay. And you don't need potentials or anything from that. When Chandramani Batash is asking, mirror have to be linear. Look, we are working with normal linear mirrors, no non-linearity, nothing. It is just you can work with nice silver plate, which is well polished, so that it will reflect anything that is thrown on it. Nothing more than that. Is there any equilibrium with molecules and photon gas? Certainly, that's the whole point. Otherwise, you will not be able to do any thermodynamics. So we are assuming the main point is that we need a medium which will equilibrate with photons. So it has to interact with photons. And more technically, the equilibrium, you have to think about the equilibration time and stuff like that. But that would be too technical to discuss it right now. But if you look at the papers, like 2010 Nature Physics paper, where this experiment was first reported, Bonn University, Colliers and co-workers. It's a very popular paper. You'll find it on Google. It's a very, very popular, very well quoted paper. You will get more details on this. So, yeah, so can you give the reference of the paper in which BC of photons? Yeah, so that is the paper which somebody has posted here. Yeah. Yeah, so can we get this PDF for future reference? Sure, I will share this. So I've written an article on these kinds of aspects. I will share it with this QIQT, mail, so that if people want, you can write to them and get it. Okay, so Yash is asking that what photons do not interact among themselves. How is the Boltzmann distribution achieved in photon gas at state of equilibrium in mirror cavity? Yeah, so the point is that photons themselves don't interact with one another, but they are interacting with the medium. Okay, it's like I don't interact with my family members, but I'm interacting with my neighbors, and my neighbors are interacting with each of my family members. Okay, and my neighbors, they are like my heat, you can say, thermal reservoir. So I am in equilibrium with them all the time, in a way, Okay, so that is, you can say, a simple way, sort of working answer. Strictly speaking, you can effectively, in presence of a medium, if you have a medium which is like well distributed like a gas, then you can effectively write a photon, get a small photon interaction also. Okay, that's what, like when we wrote this work some years back, that's how we think of this Hamiltonian. But then there are two ways. These are two equivalent ways of looking at it, and they give you same answers. Okay. So then we have Vijay, who is asking, no, Vijay, your dagger A is equal to number of photons. It is a dagger of K dotted with A of K, sum over all K, that is equal to total number of photons. You need this A and A dagger combination together. Otherwise, see, simple answer is that A dagger is not a Hermitian operator. Photon number is a real number. And we need a Hermitian operator to represent a physical quantity. How do you construct a Hermitian operator out of A and A dagger? The only way you can write it, or one of the ways, is A dagger A. Other ways A dagger, but you can convince yourself if you play around a little bit that A dagger A is the correct choice. You cannot get correct answers with A dagger. You have to do some changes. Some manipulation is required. Okay. Then Abhinav is asking that you said that interaction with the medium is energy preserving, but then how will that decrease the energy of photons? Well, it is, I mean, okay, I should be, it is energy preserving, but how should I put it? See, there will be some absorption for sure. So these are like, when you say that it is energy preserving, see, in thermodynamics, you talk about average, like average energy is preserved, but there will be some fluctuation, right? I mean, there is an average temperature, but if you measure temperature of any body, there will be fluctuations. So it is energy preserving only in the average sense. There will be some fluctuations. Otherwise, yes. Otherwise, it's like a mirror. There is no fluctuation, right? So when I'm telling that the number of photons is conserved in the cavity, I mean the average photon number. But certainly there is a fluctuation in number of photons also, which you can calculate. So then we have Sumimal Da is asking, in your diagram, Fabry-Perot cavity, why do you have boundaries other than mirrors? You should not have only mirrors. Yes, that's a technical question. I appreciate. You can also have other, I mean, you can have other cavities also. Like we did some work where we had this cylindrical cavity. So, and that was sort of slightly easy to treat, I mean, easy to deal. Fabry-Perot, people may ask this question that Fabry-Perot cavity then has to be infinity in X and Y direction if mirrors are on Z direction. And I didn't want to bother with infinities right now. So I am working with cylindrical cavity. But yes, technically, I mean, the proper answer is yes. If I'm telling it's a Fabry-Perot cavity, then it should be unbounded from other two sides. Yes, but to take it to 0K, that is K equal to 0, you will have to decrease the average energy also, right? Well, see, you have to see what one is trying to do is one is trying to redistribute energy. That's what equilibrium and all is, right? You will decrease the average energy for sure, but that, see, the reservoir is certainly going to take some amount of energy. I mean, eventually, I mean, if you take temperature going to zero limit very gradually, then that's the whole game, right? I mean, you want this work to be done by your system so that there is a net heat flow outside. Yes, certainly. But again, this is the average. What I'm trying to tell you is that the average energy sort of is going away. It's not the energy in each collision that's what one is talking about. And it is done in a very, very gradual way. It's done adiabatically, sort of, so that you are in equilibrium at each instant. That's like the point. Is symmetry breaking related to superfluidity? Of course, this is an example of superfluidity. In fact, the title of this, one of the papers, is that they have generated a superfluid of light. It's very fascinating. But yes, that is very closely related to superconductivity and superfluidity, of course. Chandramani Batash, do this quantum mechanics? Of course, Heisenberg equation of motion is always sacrosanct. It's always, we better be satisfied. Otherwise, it's people. I mean, otherwise, it's whatever we are talking about is nonsensical. See, the subtle point here is that the ground state need not respect symmetries. Keep that in mind. The equations of motion better be obeyed all the time. But who told you to assume that the ground state should also obey the symmetries? Nambu, who was the first man to bring this to fore. Historically, Heisenberg said that in magnetism, see, the magnetism Hamiltonian is rotationally invariant, but then you have magnets which get aligned, where all the spins get aligned in one direction, and you have a large, like a domain, So that was one of the first examples. I think the first example, proper example, where you saw symmetry breaking.
You can close it here because the next will start.
Sure.
So let us thank Vivek for the very nice presentation. And if anyone of you have any query, you please write to Vivek.
Sure. Thank you. Thank you all for joining. It's my pleasure. Have a good day.
So I hope the next speaker has joined. Okay, he's here. So could you please share your slides? Sustain, please share your slides. You are muted, so please unmute yourself.
Okay, now, sorry. Okay, now it works.
Good morning.